Hello, I'm Mridula, and this is my lab video 1, Constant Velocity for Physics 2111. So what is the purpose of this lab video? The purpose is to observe an object moving with a constant velocity and to create a model of the motion of the object using a tracker. Next, to create a computational model based on Newton's second law of motion. And finally, to compare both the models using a graph. The principles used in this video are Newton's second law of motion, which is the rate of change of momentum which is directly proportional to the force applied. So for the ball to be in constant velocity, the net force must be zero, which means that the force exerted on the ball and the force of friction are equal to zero. Therefore, the momentum is also constant. So if we look at the equation over here, the net force is equal to delta P by delta T. And if we rearrange this equation, we get the momentum update formula, which is the final momentum equal to the initial momentum plus the net force times delta T. And if we divide this equation by mass, we get the velocity update formula, which is Vf equal to Vi plus net force divided by mass into delta T. Next is the position update formula. This is the most important formula as we use this formula to find the final position of the ball in GlowScript. So in this formula, we rearrange the average velocity equation to get the final position equal to the initial position plus the average velocity times delta T. In this experiment, I use a tennis ball, which is the system, and it is rolled on a wooden dining table, which is the surrounding. The initial conditions of the experiment are the mass of the tennis ball is 56 grams, the initial position is 0 in all dimensions, the initial time is 0 seconds, delta t, which is the time step, is 0.033 seconds, and finally the frame rate is 30 frames per second. In this slide, as you can see, I used a tracker to track the motion of the tennis ball in constant velocity. So first, I used a calibration stick, which is along the length of the 1 meter roller, and then I used the X and Y axis. In each frame, I manually tracked the center of mass of the tennis ball until it stopped rolling. And as you see here on the right hand side, in the position versus time graph, you see that the line is straight and uniform, which means that the ball was in constant velocity. So to calculate the average velocity, I did 0.5 divided by 0.6, which gave me 0.833 meters. And these are the values in the data table. So you can see the x values, which is for the position of the tennis ball, and then the t values, which is the time. So I used these values in the data table to create a computational model of the tennis ball in constant velocity using GlowScript. In this slide here is my code in GlowScript using Python. So t is equal to 0 and delta t is 0.033 seconds, as that was the value I used in my tracker. And t less than 1.6 is the total time taken for the tennis ball to stop rolling. And the net force here is of course 0, as we assume that the ball is in constant velocity. To find the final position of the ball, I used the position update formula, and using that formula, I got 0.027 as the final position of the tennis ball. So once I run the code, this is the diagram I get, and this is the position versus time graph, the computational model. So as you can see, the velocity is constant, and the total time taken is approximately 1.6 seconds. So here is the data and model comparison. So the x-axis is the time and the y-axis is the position. The blue line is the observed position of the tennis ball found using a tracker, and the orange line is the predicted position of the tennis ball found in GlowScript. So as you can see, they start off the same, but then the lines diverge towards the end. The reasons for why the lines diverge towards the end could be that the placement of the point of mass may not have always been at the center of mass of the tennis ball. The computational model does not account for the friction experienced by the tennis ball against the table. And finally, we also do not account for the uneven surface of the table. What if the positive x-axis and the negative x-axis were changed? then only the slope of the graph would change, and it would be negative as the tennis ball would be rolling in the opposite direction, but the absolute value of the slope would still remain the same. It's not possible to tell how many forces are added for the net force to be zero, as the tennis ball could have collided with the air particles. So the only forces that we can account for are the initial force of the hand which is rolling the tennis ball and the force of friction. Thank you guys for watching.